This is a lecture at a kind of unusual hour of the night for me, so let's see how this works. Alright, the sound is going, good. Okay. So, we missed our lecture yesterday due to some unforeseen technical difficulties. I think I have everything fixed. Let's hope it works alright today. Anyways, we're into 4.3, a section that sort of feels like a little bit of an unfortunate diversion from the story of complex analysis we've been telling so far, but it is something that we really do have to talk about at some point. It wouldn't be a complete complex analysis class without it. And what that is the connection of what we've learned so far involving the calculus of residues with some decidedly non-complex analysis-y type topics like the calculation of certain integrals or series, or limits of sequences, things like that. Real analysis stuff to do with just real valued functions. And so in particular, the evaluation of otherwise difficult definite integrals can be accomplished relatively efficiently in certain cases by using some things like the residue theorem. Namely, the residue theorem says that an integral around a closed curve can be evaluated by computations involving the integral at a few points inside the curve, or of the integrand at a few points inside the curve. This is kind of cool, right? So you can evaluate along an entire curve at just a couple of points, kind of nice. The deformation theorem, on the other hand, says that the resulting value doesn't change as the curve is shifted so long as no singularities of the integrand are crossed in the process. That is, if you have, say, got a singularity here, you've got some curve around it. I can wiggle this curve, some singularity of a function f, right? And this is a curve that I'm integrating around. I can wiggle that curve a little bit, take it like, instead and like turn it into, like this. And that's totally fine. I'm going to get the exact same thing because I didn't cross this singularity, right? It just, like, I'm bending around those points, right? So as long as I don't pass through them, nothing bad happens. That's kind of the story. And so this is a really good trick to have. These results, when you put them together, make the calculus of residues a powerful tool for the evaluation of certain definite integrals. And in particular, a lot of these have no obvious connection to complex analysis. So it is kind of cool to see the gap bridge between some real analysis topics and some complex analysis ones. However, it doesn't really advance our story of understanding what continuous differentiability plus the Cauchy-Riemann equations, i.e. analyticity, gives you, right? Everything so far has been about what those two things together give you. And here we're going to break away from it. So this will be slightly less of a focus. And since this lecture is a little bit late, I might cut a problem or two off the homework. I don't know. We'll see. We'll see how far we get tomorrow. We'll go through a few of these techniques. There's not there's a modest overarching structure, but I would say that by and large, it's like, hey, here's just kind of a collection of good tricks you could use if you wanted to try to address some of these things. This is a really long section, actually, which is kind of crazy. Same with the next section. They're just kind of I'm not trying to say anything bad about this section. What I'm trying to say is that it's not exciting to me, It's not the coolest part in terms of the story of complex analysis that we've been telling. So we need to cover it because it's very important in other areas. This is a great tool to have in your toolbox, and it's wonderful to know about it. We will briefly introduce the Fourier transform, but only as it relates to certain integrals. But we'll rush through it to the greatest extent possible because it does just kind of distract from the cool story we're trying to tell. But it's good to know. So, okay. Anyways, first type that we're going to talk about is rational functions of sine and cosine. So rational functions of sine and cosine. Okay, fair enough. Just remember really briefly that sine in the complex plane was sine theta is e to the I theta minus e to the minus I theta over 2I, right? If you put like z in there, this is also true, right? We're just putting a theta in there. I don't know. And if you look, imagine, say, that e to the I theta is your curve, right? It's like a function of theta. Maybe you're going from like 0 to 2 pi or minus pi to pi, like, integrating around a, circle or something. Notice that this is just z minus z to the minus 1. That is 1 over z over 2i. Similarly, you can rewrite cosine in the same way. And then if you have some sort of a function involving sines and cosines, you can just, if you're doing an integral, a regular old real definite integral, then you could maybe replace the sines and cosines by a complex function like this, right? And then consider that guy on a contour integral, where the curve is e to the I theta, and then you'd recover your sines and cosines. So this is basically the trick. We're gonna just think before about how we even started with contour integrals, which is we started by saying, hey, I want to integrate in the complex plane, what gives? And, the problem is that it's like we're in 2D world. Are we going to do 2D integrals? And, you can do integrals on R2 and everything. You can do integrals on Rn. But what we instead did is we basically just borrowed our machinery from Calculus 1 even, and just carried it on into the complex plane by looking at kind of like one-dimensional little pieces of it, so to speak, like little curves, lines, right, in the complex planes, contours, and integrating along those things. Those were like the little adapters we plugged in so that everything we'd used before could carry through. So we're just going to essentially start with something that already has an adapter in there, and then pull it out so we can use the residue theorem quick and see what we get. All right, let's start. So example 4.3.1, this will kind of give us the general technique. I will skip some of the explicit computations because you can see them on the screen in front of you. So we're going to let a be a positive real constant not equal to 1. And we want to evaluate the definite integral from 0 to 2 pi of d theta divided by 1 plus a squared minus 2a cosine of theta. Let's call that quantity I. Okay. So if we want to do this, let's let z equal e to the I theta. Totally reasonable, basically like what we were just saying, and we'll let gamma be the unit circle centered at the origin. Okay, then dz is I e to the I theta d theta, which is just iz d theta for the substitution z equals e to the I theta, right? Okay, so do this change of variables quickly. Okay, just punch it on in. Now cosine theta just turns into 1 over 2 times z plus 1 over z. We can see that chunk right here. Okay, now dz just turns into 1 over iz, right? Or I mean d theta turns into 1 over iz dz. That's the sum piece. And then notice we're just getting the rest of it here, right? The rest of it just carries on through. Bada boom. Now we're just going around gamma. Okay. Take that 1 over I, pull it out front. We're still integrating about gamma. Just do a little bit of algebra. We get z plus a squared z minus a squared az squared minus a. Do a little bit of factoring. This turns into the integral around gamma of I dz divided by the quantity z minus a times the quantity az minus 1. All right. Then if we just do a little bit more factoring, nothing fancy, we're just going to pull an a out of the second term. We get a times the quantity z minus a times the quantity z minus 1 over a on the bottom right there. So this quantity on the bottom right there tells us where our poles are at. Or, like the poles of the integrand, right? We factored it so we can see when the denominator is 0. These are simple poles. One of them's at z equals a, the other one's at z equals 1 over a. Pretty obvious from that, right? So we just calculate the residue. Okay, so the residue of I over, the function we just factored on out at a, and then that guy at 1 over a, right? Okay. Oh, is this lagging on me? I hope it's not going to crap out. Oh, man. Let's see. So all we're going to do there, remember, for this is we basically just take this root and plug it into the other piece, right? Like just get rid of that one for all intents and purposes, right? So this will be I over AZ minus 1, and we're going to evaluate that at Z equals A. So we'll get I over A squared minus 1 for the residue there. And then we do the same thing on the other side, I over A Z minus A. That's this first piece. It's the thing that 1 over A isn't a root of. And we evaluate that at Z equals 1 over A. So I'll get I over 1 minus A squared. That's the residue there. Okay. Now all we have to do is notice that if A is between 0 and 1, then it's inside the unit circle centered at the origin, and 1 over A is outside. In that case, by the residue theorem, this integral right here about gamma, well, that'll just be the residue inside the curve. So that one is going to be I over A squared minus 1, since A is inside the curve, right? Z equals A is the point inside the curve there. And so we just do, I'll get 2 pi I from the residue theorem times that residue. And if I actually put it all together, I get 2 pi over 1 minus A squared. All right, cool. Now, if A is bigger than 1, A is outside of gamma and 1 over A is inside, do the exact same thing, plug it on in, 2 pi over A squared minus 1. End of example. Easy. So that's kind of the business. My dog is sleeping behind my chair. I almost ran him over. Little guy. Okay, so here's basically the summary of what that is. If you have, this is proposition 4.3.2. So if you have r of xy, a rational function of x and y, two real variables, whose denominator does not vanish on the unit circle, then, and that part is important, whose denominator does not vanish on the unit circle, and it has to be a rational function of x and y. All right, in that case, then, the integral from 0 to 2 pi of r with cosine and sine plugged in for x and y is 2 pi I times the sum of the residues of f of z inside the unit circle. What is f of z? F of z is 1 over iz. This is just like in this example from this change of variables right here, when we're changing d theta into 1 over iz times dz. Okay, so that's where that iz comes from, 1 over iz. And then we just plug in, well, these other forms of sine and cosine, where you plug in, z for the e to the I theta, right? So you just plug that on in, and then you can get this nice formula involving the residues of this bad boy, which is, if you notice, exactly what we ended up doing up here. I know it looks super complicated when you write it out like in this proposition, like that looks like a nightmarish function. It's just not actually that bad to use though. It's just like this. You have to calculate a couple of residues. Honestly, that's the hardest part. All right, fair enough. Now, the next thing we're going to talk about has to do with improper integrals. So improper integrals, if you don't recall, are integrals where one of the bounds is infinity, which is not, in fact, a number in the real numbers. So these are improper in the sense that that properly is not a number, right? And they're just defined in terms of a limit. So the integral from a to infinity of f of x dx is the limit as b goes to infinity of the integral from a to b of f of x dx. Exactly the same on the negative side, right? And then if you want to go over the whole real line, I'm going to make this a little bigger so it's easier to highlight. If you want to go over the whole real line, then this you just break it apart into saying, hey, for the integral across the whole real line to exist, each of those two parts have to exist, and we have to add them together. That is the integral from 0 to minus infinity of f of x dx, and the integral from 0 to infinity of f of x dx has to exist. And you sum them together to get the integral from minus infinity to infinity of f of x dx. Fair enough. Now, you can, once again, you can just replace those with the limits that define them, and then you have, sum of two limits. All right, so once you know that these guys exist independently, then you can use a special convenient form of the limit to evaluate it quite often. That is, instead of doing this limit right here and then this limit right here by themselves, you can do them both at once in a single limit. So think of it like this. Limit from minus infinity to infinity of f of x dx. Well, just like we wrote, this is the limit as a goes to infinity of minus a to 0 f of x dx plus the limit as b goes to infinity of the integral from 0 to b f of x dx, well, you could think of that as the limit, as the limit of a and b jointly going to infinity, of the integral from minus a to b of f of x dx, right? So this is a limit where the a's and b's are like pairs, right? Okay. Now, if this all exists, this is all fine. And this last piece right here is the piece that you have to be careful not to do this if you don't know that this guy exists in the first place, or at least that these two things separately exist, right? If you know that this exists, then you can figure out what it is by evaluating it in the form of this limit, which is the limit as r goes to infinity of the integral from minus r to r of f of x dx. So when you know it exists, you can do this, and it is often very convenient for us. So if this limit exists, then the here's what I should say. If this just to be clear, this is not a complex analysis theorem. This is one you've probably seen in, I don't know, calculus 2, I'd imagine, something like that. If the limit as a goes to infinity and b goes to infinity of the integral from minus a to b of f of x dx exists, then the improper integral on the entire real line of f of x exists and is equal to that limit. So, okay. But remember, this has to exist for this to exist, right? So be careful on that. All right. So one thing you can do, though, to get the existence of stuff like this is to just do a comparison. This is often one of the easiest things you can do. This is, once again, not a complex analysis theorem, but still useful all the same. We will use it very shortly for an example. So if in absolute value, not modulus, because we're back in the real line, suppose that f of x in absolute value is less than or equal to g of x for all x greater than or equal to some value a, and that the definite integral from a to infinity, improper definite integral, of g of x dx converges to a finite number g. That is, it exists and it equals g, big G. Then the integral of f of x from a to infinity dx, this improper definite integral, also converges and in absolute value is less than or equal to g. And you can do the exact same thing for integrals along the left half line or over the whole real line and so on, right? So basically, if you can compare it, say, hey, this guy in absolute value is smaller than something, and if I integrate that guy on the same improper domain, then that exists. So if I integrate this guy, that exists. Basically, just because integrals, remember, measure, definite integrals at least, measure areas. So if something has like lower height everywhere, then over the same width, it's got, if one of them has finite width, the other one has to as well, right? That's the entire deal. Okay, let's use this. So we'll use this in a little example right here, which is kind of cool. Okay. So we'll start with, oh, I'm on the wrong layer. This guy. Okay, example 4.3.5. We're going to evaluate the improper integral from minus infinity to infinity of x squared over 1 plus x to the fourth, that quantity, dx. Okay. So the first thing we're going to do is we're going to establish that this guy does indeed converge. Then we're going to make use of the most useful form, which will be the limit as r goes to infinity of this guy from minus r to r, right? Okay. So the first thing we'll do to show that it converges is to note that the integrand is, for one, even and continuous. So it suffices to show that it converges on the half line, because on the other half line, it also converges, right? Okay. It would also converge because it's even, so it would be the same, right? Okay. So all we have to do is show that, say, the integral from 1 to infinity of x squared divided by the quantity 1 plus x to the fourth dx converges. Now, we can do this just by a comparison. We'll just say it real quick. Notice that if you integrate 1 over x squared from 1 to infinity, well, that's just the limit as b goes to infinity of the integral from 1 to b of 1 over x squared, which is just, what? Minus 1 over x, right? Okay, so just do that, and then if you take that integral actually, you get, or I mean, that's, minus 1 over x evaluated from 1 to b, right? And so you get minus 1 over b minus a minus 1 over 1, so that's plus 1, and you just get out, as b goes to infinity, well, that first term drops away and you just get out 1, right? So since this guy, 1 over x squared, notice x squared divided by 1 plus x to the fourth, well, if you just kind of look at like the ratios of the terms, you have like a squared over a fourth, right? You can go through and prove this out quite nicely and say, hey, look, 1 over x squared is larger, and so on, than x squared over 1 plus x to the fourth for values of x greater than 1. Pretty easy to go through and actually write that out. If you want, you should do it as an exercise. Just a couple of inequalities, simple manipulation, but just intuitively you should expect it because you have a squared over a fourth, right? So 2 over 4, it's like 1 over 2, and hey, bada boom, right? Okay, cool. And there's that little extra plus 1 down there, so it'll be smaller. Okay. Now, since our integral converges, we can use a symmetric limit to evaluate it. That's the entire reason we went through all this business. Now, we'll denote our integral by I, and we'll write this integral from minus infinity to infinity, which we know exists by that previous little proposition that says that, hey, if you can compare it with something that does, then you also exist. Okay, cool. In fact, what we're just doing is we're combining this guy right here with the comparison proposition 4.3.3. Okay, so now that we've done that, we're just going to do this as the limit as b goes to infinity, or sorry, should be an r, I believe. An r goes to infinity. I hope it's not written wrong in the textbook. That'd be an unfortunate gaffe on the author's part. But it should be an r, if that's not clearly an r. Weird. Okay, all the same. That is as r goes to infinity of the definite integral from minus r to r of x squared divided by 1 plus x to the fourth dx. Okay, so this guy, how are we going to do this? Well, what we're going to do is we're going to say, hey, the interval of integration from minus r to r in this, right here, minus r to r, this little piece, we're going to consider this as a path, let's call it gamma r, along part of the real axis in C. That is from minus r to r. This is gamma r right here. Okay, now we can make this into a simple closed curve by forming this little half circle, let's call it mu r, this little component, taking us from r back to minus r along the top of a circle, right? All right, cool, circle of radius r, easy. So put them both together, let's just call that capital gamma r, right? Where we're adding curves by going down one, then up the next. Okay, so this is a closed curve, easy, nice. We could have also done this using a circle on the bottom if you want. Nothing wrong there. We could label these differently and make ourselves a new curve. We're gonna use this one right here. Good exercise. I think they show the work in your book if you want to see it. You can compute that it works the same right here if you want. You don't need to if you don't feel like it, but it suffices to get the answer one way. You don't have to show it that you could do it a different way if you felt like it, but it is a good exercise to do that. So here's our little circle. Now notice along gamma r, the integrand is the same as the function z squared divided by 1 plus z to the fourth. That is, along the real axis, plug in real values into f of z right here, and just, you might as well replace them with, z's with x's, right? They're real numbers, right? Real numbers are in the complex plane. Okay. This guy, though, if you look, is analytic everywhere except when z to the fourth equals -1. That is, except for the fourth roots of -1, at which points this guy has simple poles. So the 4 poles of this guy you can just write out. Remember, these will be fourth roots of -1, right? They're still roots of, well, negative unity in this case, but they're evenly distributed about the circle, right? And so you'll have 2 of them up here and then 2 of them down low. When r is strictly bigger than 1, these guys will be inside the circle. If you do them smaller, then they'd both pairs would be outside, right? But if r is bigger than 1, Then they go on inside here, and by the residue theorem, I can evaluate this integral by taking 2 pi I times the sum of the residues of this function f of z at those points. Easy, right? Okay, so let's just do it with those top guys. And in fact, we can calculate the residue of f at all of those points really easily, right? Just because the residue of f, it's got a simple pole. So I'll just take one more, I'll take a derivative on the bottom, right? So I'll get 4z to the third and z squared up top. Just plug in zk. So I'll get zk squared divided by 4 zk to the third, where zk is the kth root of -1, right? Just like we wrote out up here. Okay, so that's 1 over 4 zk. If you just take the squared on top and the third on the bottom, we just end up with 1 zk on the bottom. Okay, so 1 over 4 zk. Easy enough. That's a great formula for the residue. Super convenient to work with. Now, the residue theorem, like I just said, tells us that the integral of f about big gamma, this closed curve, is 2 pi I times the sum of those residues. We could also use the other residues if you want, and you can go double check that you get the same thing, but I promise you do. And you'll get 2 pi I, and then since we have that 4, we might as well just pull it on out. So I'll get 1/2 pi I, and then the sum of e to the minus pi I over 4 plus e to the minus 3 pi I over 4. Those two ones, that is z1 and z2, the first two roots of -1 right up here. Okay, now sum those guys up. Just, do a little canceling, pull out an e to the minus pi I over 2. Take those guys together, just do a little bit of algebra, and you end up with pi over root 2. So that's true for every r greater than 1. So for the two pieces of the path, you have exactly this, right? So over gamma f of z dz, you get out pi over root 2, right? Okay. Everyone following so far? So big gamma, we integrated around big gamma and we got this. Now notice, because going here and then here, right? On the r part, it's exactly the same as what we want, right? On this little gamma, integrating f on the little gamma is the exact same as integrating the function we started with. Okay, so now all we have to do is piece things together. That is, along mu r, the circle part of it, the top part, along this piece, we know we have what we want. Up here is what we need to deal with real quick. Okay, now when modulus z is equal to r greater than 1, then notice f of z in modulus, that's equal to r squared divided by 1 plus z to the 4th, or something like that, right? Okay, because you can put the modulus up top, and hey, just go through, do a little bit of inequalities, and you get r squared, this is less than or equal to r squared divided by r to the 4th minus 1. How do we do that? What do you think? Reverse triangle inequality? Yeah, reverse triangle inequality, right? Oh, boom, boom, boom. Easy. Okay, easy enough. And there we are, r squared divided by r to the 4th minus 1. Thus, when we integrate along here, well, that'll be less than this. Oh, wait a second. This is that very old theorem we did where we said, hey, if the modulus of an analytic function is less than or equal to some constant along curve, then you just get that, well, the integral of this whole thing along there, it will be that value, that upper bound, times the length of the curve, right? You remember this old proposition, lemma? I don't remember what we labeled it. It was from quite a while ago in chapter 2. But it's been pretty consistently useful. So, okay, just multiply it all out. What is the length of mu r, right? It's half the circumference of a circle of radius r. And so we get out pi r cubed divided by r to the 4th minus 1, that whole quantity. Now, as r goes to infinity, look, the bottom is going to definitely grow much faster than the top, right? A 4th over 3rd power. Okay. And you can show that using all the standard calculus 1 type techniques if you want, just the formalism. And then, of course, this just means that this guy the modulus of it goes to 0. So if the modulus goes to 0, then the thing inside must also go to 0, because the only thing with 0 modulus is 0. So the limit as r goes to infinity of the integral of f about mu r dz, that top half of the circle, is equal to 0. Putting the pieces together, well, if you integrate over gamma r as r goes to infinity, we'll get the limit as r goes to infinity of f about mu r, and the limit as r goes to infinity of f about gamma r, little gamma. And hey, what is the integral of f about little gamma? Well, that's what we're trying to find, and we know what it is about the big one, right? It's just pi over 2, so you take a limit as r goes to infinity, and that doesn't change, right? That doesn't change at all. We're not getting any new residues or anything like that, right? Okay, so bada boom, look, here's the piece that we just showed goes to 0, and then we have the limit as r goes into infinity of this piece, which we've said exists. We've shown that at the beginning, so that is exactly what we wanted to calculate. And don't you know it, we have that the improper integral from minus infinity to infinity of x squared over 1 plus x to the fourth dx is pi over the root of 2. Oh, that's an amazingly cool little trick, isn't it? How about it? It's satisfying to see this technique used. It's not really so much a part of the story of complex analysis in the sense that it tells you about the consequences of analyticity or something like that, but more so it shows you that knowing about just how many powerful things you get out of Cauchy-Riemann plus continuous differentiability, knowing about that wealth of information you get, that extremely overpowered wealth of information you get from such minor assumptions, lets you do a lot of things that you otherwise might not be able to do easily. And this is kind of a great example of that. So just think about the key elements that made this example work. One, this is the first thing we need to do. We had to establish the convergence of the improper integral so that I could use a symmetric limit for the evaluation. That is the limit as r goes to infinity of the definite integral from minus r to r of the stuff, right? Okay, so we had to do that first. We have to establish convergence first, so we can use a nice form. Okay. Now we need finitely many singularities in the upper or lower half plane with none on the real axis, so they could all be enclosed in big gamma, or if you want to do, say, like a big lambda or something like that and do this example right here, you could. So they could all be enclosed in there for large enough r. Question, why didn't it matter that when r was less than 1, these guys were outside of it? Why? It's because of this limit right here, to be clear, right? If finitely many things at the beginning are a problem, or even infinitely many things at the beginning are a problem, it's not really a big deal if after some r it's not a problem anymore. So there our r was 1, right? Okay, fair enough. So finitely many singularities either above or below the real axis, so you could do this circle trick or half circle trick. Okay, then we needed finally an estimate showing that the integral along the upper or lower part of the circle went to 0 as r went to infinity. And then we were able to get rid of that chunk and only be left over with the thing that we wanted to evaluate in the first place. Okay, so these three pieces right here are basically what we need to do stuff like this, and we sum it up in a proposition here. Proposition 4.3.6, 3 different parts, very wordy, basically summarizing exactly what we said. So part 1, suppose f is analytic on an open set containing the closed upper half plane, that is the half plane, everything above the real axis, including the real axis, right? Okay, so above the real axis and including the real axis, except for a finite number of isolated singularities, none of which are on the real axis. Now we also need positive real constants m, p, and r naught with p greater than 1, f bounded in modulus by m divided by z to the p in modulus, whenever z is in the upper half plane. Okay. and z is at least as big in modulus as r naught. Okay, so it can maybe not be true at first for small modulus z, but for sufficiently big modulus in the upper half plane, it's true. All right, cool. In that case then, the integral from minus infinity to infinity of f of x dx is 2 pi I times the sum of the residues of f in the upper half plane. That's exactly what we just did, but this is the confusing way to state it, right? All right, why do we need this piece right here? That's to get rid of the piece that we don't want, this estimate, right? Realistically, we don't need m divided by z to the p if we don't want to. There could be other ways to get there, but this is a good form. All right, cool. Now we can do the exact same thing with the replacing h with the closed lower half plane. That is everything below the real axis, including the real axis, and then you get exactly the same thing if you, of course, modify everything accordingly. All the h's, replace them with l's, right? Okay, in that case, exactly the same. Integral from minus infinity to infinity of f of x dx is minus 2 pi I times the sum of the residues of f in L. And then finally, both of these formulas hold for sure if p is, or if f is equal to p over q, or p and q are polynomials, the degree of q is at least 2 greater than that of p, and q has no real zeros. Well, hey, that looks exactly like what we were doing right here. Yeah? In fact, that is the case. So basically, it gives us at least one where it's a little bit easier, though notice part 1 and part 2 properly subsume part 3. Part 3 is just a convenient subcase of 1 and 2 that is very easy to check, right? All right, because when q is at least of degree at least 2 greater than that of p, then notice you can definitely do this bound right here for all big enough values of z, right? I mean, you can really do it. Yeah, that's fine. Just to say for all big enough values. I don't want to dwell on that more. Next time, what we're going to get into is we're going to start talking about, oh, did I not put all these together? Yeah, okay, that's good. That's a good, we'll just leave it very vague for the moment. The Fourier transform. We'll talk about integrals of Fourier type. So Fourier transforms, you probably have seen before if you've taken differential equations or maybe a few other different classes. They're used kind of a lot. Fourier transforms are defined as follows. You take a function f from r to c. Now, there maybe are some conditions you have to use to make sure that this makes sense to define them like this, but only for certain types of functions. But you make a new function defined for a new number, omega, either real or complex, and you use it in terms of the improper integral. So a function f gets sent to f hat omega, or if you want to use script f of f omega, just a new function of a new variable, which is defined to be 1 over the square root of 2 pi times the integral from negative infinity to infinity of f of x times e to the minus I omega x dx. So we'll look at some nice tricks we can use to solve integrals that can sort of be written something like this. And if you are looking at this definition right here and saying, I learned the Fourier transform differently, don't worry, there are a bunch of different ultimately not big deal differences in terms of how people do this, and we don't need to care that much about the Fourier transform. Just knowing it exists will basically do a couple of nice tricks that people use all of the time in harmonic analysis to deal with the Fourier transform, and all of those tricks will really come from applications of the residue theorem and the deformation theorem, of course. So we'll get into that next time. The rest of the chapter is just a similarly eclectic bunch of different tricks, kind of vaguely related, all with a similar theme of, hey, deformation theorem plus residue theorem, and then some weird algebraic manipulations. Normally not that weird, but just kind of a grab bag of different tricks. So we'll go through some more of them. We'll see how far we get. It is a long section. I think we will be able to touch on almost all of them still, but it since it's not super clean in its entire presentation, if we miss one or two of them, you don't miss out on too much. So we'll do what we can, and don't stress too bad. This will not, of course, be like a super gigantic focus of the next exam, though I may ask a problem or two using some of the less nightmarish techniques that will come up. But overall, the focus of the class is on the story of complex analysis, not on the story of the cool tricks it allows us to do in real analysis. So, good introduction to the things that complex analysis enables outside of complex analysis. And sorry for the lecture being a day late. It has been a crazy week, and I had some tech difficulties with my computer. And also, I bought a house. So today, actually, we closed. So it's been a wild time. I think that's a good time to end this video, and see you next time.